Monday yet again.
We have 2 Mondays left.
We have 2 Mondays left. We've only got 5 lectures left. That means we've had about 35 lectures of organic chemistry already.
That's good or bad?
That's a lot. It's sad. We're coming to a close. Our theme song today, I thought of at my office, is Nightswimming by REM. I thought it pertinent before an exam. Do people still go swimming? Clearly not a good one. All right. So let's see. The exam is when? Exam is Wednesday. The final is when?
Next Tuesday after that.
Thursday night.
3 Tuesdays from now, right?
Yeah.
Yeah. So we're pretty much 2 weeks out, which is awesome.
And then you have to take
Office hours for the next couple of days. So today, it's going to be 3 to 4. That's a little different than it's been in the past. We got booted out of our room for half an hour, so 3 to 4. And then tomorrow will be 11 to 12. Both of those are in room 2018. Okay, so that's our office hours. Let's see. You guys want to know anything about the exam?
Sure. Questions.
So, the exam. On the practice exams, there are 3 spectroscopy problems. That seems like a lot to me. 1. I'm going with 2. So 2 spec problems. I'm very uncomfortable with almost half the exam being spectroscopy problems, and so I've eliminated 1 of those. So we're gonna have 2. I've made up for it in other areas. Don't worry. Another thing that got pointed out to me, and I want to make sure everyone knows this so that we're on the same page. So when it comes to allylic halogenation, and so specifically when we are discussing major, minor products. All right, so here's what happened. I've never taught radical reactions, and I also haven't referred to the book once. And so I messed up on this part. What do you think that's going to be on the exam? No, there's going to be no. Now, it's fair for me to ask you for what possible products are there in allylic halogenations, but I'm not going to ask you major versus minor products. That's my bad. I think if that's the worst thing I did this semester, I think we're going to be okay. So just don't worry about major and minor products on allylic halogenations. We have homework. Due when? Tonight. And then when's the final homework due? I think that's on the final Friday, so we got a little time for that. Tonight's homework is pertinent to the exam. It's not a waste of your time to do it. It's going to be some really good nucleophilic substitutions next Wednesday. So the final homework is actually next Wednesday, which some of you might have plans on Friday anyway. I've been there. Okay. So I think that's it. I might post a little more homework problems today on nucleophilic substitution, just for more practice for you guys if you want. Any other questions exam-wise? Or any questions at all exam-wise? No? Okay. Yeah? No elimination. We didn't do it. We are going to do it, but that's going to be covered on the final. So. All right, I got a good question where it's like, is the final cumulative? And so is the final cumulative?
Yeah.
Sure, but the thing is, we've learned so much since that first exam that I don't even need to ask you things like, show me the secondary carbon, because it's necessary to know the secondary carbon in the first place to know some of the reactions, right? So a lot of the stuff, a lot of the concepts from the earlier part of class, really almost the first half of class, we've done a lot with thus far, and so it's not going to be necessary for me to ask a lot of exam 1 type questions, because you got to know that stuff at this point anyway. So it's not going to be. It'll probably be a little exam 2 and exam 3 heavy, if anything. Okay, let's roll. So Let's see, we were talking about leaving groups last time, and so we talked about how the conjugates, let's see, what did we talk about? So we talked about how the conjugates of strong acids typically make good leaving groups, and so iodine, bromine, chlorine are all good leaving groups, but fluorine is not because it is the conjugate of a weak acid. So that is unfortunate. However, halogens are very nasty, there's lots of pollution, and halides are typically not good for the environment. So one thing we can do is we can try to substitute alcohols, but of course what we found is that alcohols, or just OH groups by themselves, don't make good leaving groups because water is not a conjugate, or I should say, OH, right here, is not a conjugate of a strong acid. It's the conjugate of water, and the pKa of water is like 15.7. So we've got to come up with some ways to get around that problem. And so the first way to get around that problem is pretty straightforward. You know what it is? We want to protonate it. So that's pretty much it. If we protonate our OH group, what we're going to find is we will make a good leaving group. So for example, what we'll have is we can take, say, a substrate that looks like this. And so, we'll use any strong acid. Let's use HCl. So the first thing that's going to take place is really going to be the first reaction we ever learned about. So that's going to be an acid-base reaction. So we're going to protonate our OH group. So we start an arrow where?
Electron.
At electron. So then we draw to the proton. We kick off our chlorine as such. And so in the process of doing this, what we will have now is going to be our protonated alcohol. And so let's think about this for a second. We've got a protonated alcohol. Well, that's going to be much different from a regular alcohol. And so what happens if a protonated alcohol leaves? Well, essentially, we're going to end up with water plus our R plus, whatever that is. Now, is water the conjugate of a strong acid? Yeah, because the conjugate acid of water, of course, is H3O+, and so the pKa of H3O+ is right around minus 1.7. And so, in effect, what we're able to do is we're able to turn our OH into a good leaving group by protonating it and basically changing the acid-base properties. All right, so once we've got this structure right here, what's going to happen is it's more or less going to go away. All right, so it's going to go ahead and leave. So what type of mechanism is this going to be? Should be SN1, right? Because we're not having attack from the nucleophile. And so what we're seeing is an SN1 type reaction. Now this is really kind of one of the unfortunate aspects of protonating our alcohols. That it tends to encourage SN1-like reactions. So what we're going to end up going through is a carbocation. So our carbocation will look something like this. So we've got a positively charged carbon here. So finally, when we get attack of our nucleophile, and what's our nucleophile going to be? Have we put it? Is there a good nucleophile in solution somewhere? So that is another aspect of this stuff, is the fact that, well, the nucleophiles pretty much come from the acid itself, right? We created a chloride anion, and it's still in there. And so, of course, we can get attack from either side, since we're attacking a carbocation. And so let's say we end up with this product. So let's see, is this the inversion product or the retention product?
Retention.
Yeah, so this is inversion because our nucleophile has added to the other side, right? Our leaving group was on the right side, and now our nucleophile has come in on the left side. So we've inverted our stereochemistry. But we could also have the retention product, and so we would say that we have this product plus, yeah, so we've got this product plus the enantiomer, and it's the enantiomer that is going to be the retention product. All right, so some things about protonating alcohols. It's pretty easy. It's pretty cheap, because strong acids are super cheap chemicals. And furthermore, we have a built-in nucleophile. All right, so that's pretty straightforward. All we got to do is add acid, and this thing's going to happen. But unfortunately, we've seen that it typically is going to encourage an SN1 type mechanism. So we want to make sure So we have that down as a con to protonating. So we'll say plus encourages SN1, and so this becomes messy because not only do we get attack of that carbocation from other sides, but what else is possible? We could have shifts of some kind, right? So protonating is not typically the best thing to do unless you have a substrate that is inherently not going to lead to lots of other products that could be possible. All right, so to overcome this, we're going to learn about the second way that we do it. So the second way that we do it, we're basically going to turn our OH group into something that looks kind of like this. So we're going to show this. All right, so we're going to kind of turn our OH into a different kind of functional group, and we're going to find that that ends up making a very good leaving group. Does anyone recognize kind of what this structure is? What if it's... Yeah, so let's show its conjugate acid. What is this molecule? That is sulfuric acid. Is that a strong acid or a weak acid?
Strong.
That's a strong acid. Does this mean that it's the conjugate of a strong acid or a weak acid? It's the conjugate of a strong acid. Would that be a good leaving group?
Yes.
Yeah, and so that's why this is able to turn this into a good leaving group. Essentially, this is the conjugate of H2SO4, which means now we'll have a good leaving group. Now this is organic chemistry, and so we don't typically, we like to add organic type things to our structures because we're using organic solvents, and typically we're going to find that organic things are much more soluble in organic solvents, and so that's why we need to use organic type things. So we're going to use something similar to sulfuric acid that's a strong acid, but it's going to be an organic strong acid. And so what we use is something called tosylic acid. And so you'll see that often as just TSOH. So that's abbreviated. It's for tosylic acid. So tosylic acid, what it looks like, and you're going to see some parallels. So we still have sulfur. We still have double bonds to our sulfur. But now we have a benzene ring and then a methyl group. And so what that does in effect is that's going to make this a much more soluble structure in organic solvent because we've got lots of organic-y stuff on the right side. And so now we've got something that's going to be both a strong acid as well as soluble in the solvent that we're likely going to be using. Okay, so this is tosylic acid. And we'll say it is very similar to H2SO4, mainly meaning that we've got a strong acid on our hands. Okay, so this is how we use this tosylic acid. Let's start with, say, let's start with an alcohol substrate. Let's see, we need to turn that. I need to make this chiral. So now we'll worry about chiral later. All right, so we're going to start with some alcohol substrate. Now, just looking at this, we don't have a good leaving group. It's an OH group. It's just not a good leaving group. So the first thing that we can do is we want to derive this into this tosylic acid type structure. And so what we're going to use to do that is going to be something called tosyl chloride. All right, instead of using tosylic acid, we're going to use tosyl chloride. And so what that looks like is it looks just like the acid, except instead of an OH here, we're going to have a chloride. So now we're reacting it with this molecule. And so you're not going to be responsible for this mechanism. You're just going to be responsible for seeing what it forms. I will show you the mechanism though, just to see what's going on, because we also have to use some sort of amine base. So that's also going to be in there. We're just going to use trimethylamine. And so ultimately what's going to happen is this is a relatively concerted type mechanism. So our amine base is going to attack the proton of our alcohol. And so we're going to do that, which kind of at the same time, our alcohol is going to attack our sulfur, and then our chloride is going to leave. And so you don't need to worry too much about the mechanism. You need to know that in effect what happens is that we're going to end up with a structure, our alcohol, that was, well, it wasn't just an alcohol. What it now looks like is this right here. We've just converted pretty much our alcohol into this derivative right here, which is now the conjugate of a weakened. And in fact, we don't even need to draw this out. You don't need to worry about the structure of tosylic chloride or tosylic acid. What we can actually just say, draw your substrate, and then instead of saying OH, say OTS. It means the same thing. I know exactly what you're saying. So essentially, here's what you need to know. You could say that you take an alcohol, and you react it with tosyl chloride with some sort of amine base, and you're going to make, in effect, this right here. This is the key step. This tells me that what we have done is we have converted our alcohol into a good leaving group. So that's the point of this. And so now what can happen is we can react it with some sort of nucleophile. What we have here is a good leaving group. And what makes this better than why do you think this is going to be better than protonation? Yeah, that's exactly it. So now we can do SN2, and that's going to be important because often we're trying to make one stereoisomer, and so by using tosyl chloride instead, we're able to do so. All right, so for example, what we can have is we could have some alcohol that looks like this, and so this is a chiral alcohol. We have one chiral center. And so let's say that we want to form a product. The product that we want to form is going to be this right here. And that's the only product that we want to form. So could we protonate this and somehow only form this product? That's not going to work because we're going to end up with a racemic mixture in that case. Yeah?
So we can do SN2 even though that's a tertiary carbon?
That's a secondary carbon.
Okay. Oh, yeah.
Right. Right? So we're talking about this carbon. We're connected to the two carbons on the ring, but that's it. So, yeah. All right, so what are we going to do to avoid, or to kind of have a strategy to only make this product?
Add TSCL.
We're going to add TSCL, tosyl chloride. What else do we have to add? We have to add an amine base. Trimethylamine is a safe one to go with. You could also use triethylamine. It really doesn't matter. We haven't really talked about Breaking Bad and meth and methylamine and things. I usually bring that up at some point. I guess we. All right, we'll save that for later. We'll get it done though. We'll talk about drugs at some point. All right. So let's see. So what that's going to do is that's going to convert our alcohol into our O-tosyl group. And so now, and I think it's fair for me to ask you, what could we use to convert this to this? Well, what anion do we clearly need to have? Yeah, so we need to have a sulfur anion, and so connected to that, we could have something. All right, so that'd be an anion, but can we ever add just anion? No, and so we have to have what? We gotta have a cation of some kind. What's your cation of choice?
Sodium.
Sodium, all right. So what you could, and I think this would be fair for me to ask you, basically have a box here and say, how do we convert that to that? And so you would, there's multiple answers that are correct. We've learned that a neutral sulfur is also a good nucleophile. So you could also use this, and that would be fine. We would be able to get to that product using just the thiol product, or the thiol reagent. So there could be multiple right answers in this case, because you could use any counter ion that has a plus charge, so you could use lithium or potassium, or it doesn't really matter. They're all going to do the same thing. Okay, so now what we've been able to do is we've been able to stereoselectively undergo an SN2 reaction with our alcohol. Okay, another thing about alcohols is going to be the fact, so I think it's weird that we don't cover the alcohol chapter in this class, but alcohols are pretty much the most common nucleophile that you'll see in a lot of these, so I don't know, I think that's silly, so we're going to spend a little time on it. Let's imagine we want to do this process. Okay, so this is going to probably be a nucleophilic substitution of some kind, so we always want to do SN2. All right, so we have a primary halide. Can we do SN2? Yeah, certainly. We can do SN2 here. And then we look over here at our nucleophile. So is it a good nucleophile? No, that is is a weak nucleophile. Why is it weak? Neutral oxygen. It's just not a strong nucleophile. So here we can't do SN2. So unfortunately that eliminates SN2, but we can still do SN1. All right, so let's make sure we can do SN1. We have a primary halide. Can we do SN1?
No.
We can't. And so no SN1 here. Essentially, nothing can go on here, right? No reaction can take place. We can't do SN2, we can't do SN1, and so we're kind of stuck. We're not going to see much reactivity. But alcohols are pretty special because alcohols are acidic. And so what we can do is if we wanted to carry out this type of reaction, we can do it. We've just got to make a little bit of a modification. And so instead what we'll do, how do we turn an alcohol into a good nucleophile? Yeah, so we want it to have a negative charge, right? So we can make it have a negative charge by undergoing an acid-base reaction. So what we're going to do is we're going to react a strong base. And so typically what you'll use is something like sodium hydride. And so what will happen is we will deprotonate. You don't need to worry too much about how this works. What you need to know is that essentially what you end up with is going to be some H2 gas. It's going to bubble up out of your reaction. And so essentially, this is a way that we can make sodium alkoxide, right? You've seen me use a sodium alkoxide nucleophile. We've used that a bunch now. It's a good nucleophile. Here's how it's made from a regular alcohol. So we basically just hit it with sodium hydride, which I said is a strong base. And so the hydride, and it's a strong base because what it is our H minus is essentially what we've got there. And so that's the conjugate of H2. The pKa of H2 is around, I don't know, it's like mid-30s. So we'll say 35 or so. And so it's a very weak acid, which means H minus is a very strong base. And so essentially we're able to make our alkoxide. So now what we can do is go ahead and throw in our bromide to our reaction. And so can we do SN2 now? All right, so we have we still have our primary alkyl halide, so can that do SN2? Is this a good nucleophile? Yeah, and so we can do this. So what we'll have is our SN2 reaction. And so now what we've done is we've formed the product we had hoped to, which looks like that. All right, so alcohols, we can deprotonate them and turn them into good nucleophiles by using a strong base. One other thing. So every time we've been doing these reactions, we've been doing intermolecular reactions, but that's not necessarily always the case. And so what we could have is something that looks like this. All right, so what we could do is we could hit this with some sodium hydride. And so what will happen is we'll deprotonate our alcohol. So we'll have O minus and plus here. Okay, so when we look at this substrate, yeah, Hope?
Can you use water as a base as top to deprotonate the?
No, it's just not basic enough. You'd have to use something. You'd have to use something with a conjugate acid that has a pK higher than like 20 or so.
Okay.
Yeah. All right. So when we look at this, do we have an alkyl halide? Do we have an sp3 hybridized carbon bonded to a leaving group?
Yes.
Yeah, we do. We have this primary position right here. All right, so we do have an alkyl halide. Do we have a strong nucleophile?
Yes.
Sure, right here, we definitely have a strong nucleophile. Now, all along, what we've been doing is we've been reacting two different molecules. But in fact, you can do this within one molecule itself. It's going to go through the same exact type of mechanism. Can you think of any reason, like thermodynamically, why this might even be an easier reaction to carry out than an intermolecular reaction? Yeah.
They're already like next to each other.
Yeah, so there's an element of entropy with intermolecular reactions, right? If we're going to carry out an intermolecular reaction, they have to bump into each other at some point. Do these things ever have to bump into each other? No, they're basically right beside each other already. So entropically, intramolecular reactions are highly favored. And so what we'll do, where are we going to start our arrow? At the left, where are we going to draw it to? Not to the bromine, but to the carbon. We'll kick off our bromine, and so this is just like any other SN2 reaction we've ever done. And so what we end up with is essentially going to be a new ring, just like that. I drew it, let's redraw it. Okay, so we end up with a new ring just like that. So basically that's a way, we've already seen how we can open up rings sometimes, and now we can actually form a ring in an intramolecular reaction like that. And these are pretty common. Alright, so that's going to be it on, I think, alcohols. So now finally we will finish our talk on, I don't even remember what Roman numeral this is. I think it's Roman numeral number 5. This is finally going to be letter E on Roman numeral number 5. So this is when we get to talk about solvent. It's Roman numeral 6? Okay, yeah. Okay, so what we're going to learn is really there are going to be 2 types of solvent when we discuss nucleophilic substitution reactions. And so they're all going to be sort of polar. So we're going to have polar protic. And so what is a protic solvent going to be? It has a proton, but it has a specific type of proton. So specifically, it contains an OH or an NH proton. All right, and so that is important because these 2 protons are a lot more acidic than the typical carbon-hydrogen bond, and that's going to play a factor in this. We're going to have the other possibility where we have polar aprotic. Polar aprotic solvents. And so, as you might suggest, there's no OH or NH bond in this case. So what we're going to find is that a polar protic solvent is actually going to favor SN1, whereas a polar aprotic solvent is going to favor SN2. And so we'll talk about that. We'll talk about that for a second. Ultimately, what's going to happen is if you imagine a situation where you have a secondary halide that we know can do either SN1 or SN2, and then we react it with something like NaCl, well, typically we can assume that, that it's going to be SN2 because we've got a solid nucleophile. But in this case, if you're also given a little information about the solvent, we're going to have to, let's see, we'll just say the solvent matters, and then we'll talk about how they matter. All right, so initially you might just assume it's SN2, but we're going to find that the solvent can change things up a little bit, and we'll talk about why that is. In either case, though, we're going to end up with the same product, basically substituting our chloride onto our bromide. All right, so let's think about our solvents and how they're different. Let's make two columns. So the first thing we'll do is we'll actually just list some examples. So on the left side, we're going to talk about polar aprotic. And so I'm going to talk about polar aprotic first because that's what we do that's how we do SN2 reactions, and so ultimately that's kind of the goal anyway. And so over here, we'll put polar protic solvents, and so that's going to be for SN1. All right, so some examples of polar aprotic are going to be acetone. So that's a pretty common one. So acetone looks like that. We'll also use things like acetonitrile. So acetonitrile has that kind of structure. DMF, dimethylformamide. And you don't need to worry too much about the structures, I just want to give you an idea of what they are. So that's another one, and again, so none of these cases do we have any OH or NH bonds, because that would make it polar protic. Finally, you'll see sometimes DMSO, so that's dimethyl sulfoxide, so that looks like this right here. So these are polar solvents, and we know that they're polar because we can count our dipoles in each case. We've got dipole there and a dipole there, dipoles there. So we've got dipoles abound. They're definitely polar solvents, but we don't have any OH or NH bonds that are going to make these protic. The polar protic examples of solvents are going to be mainly things like methanol. So any alcohol is going to be a polar protic solvent because clearly you have an OH bond. That means that water is also going to be a polar protic solvent. And then I guess any amine that has an NH bond, so say this amine would be a polar protic solvent. We don't typically see amines as solvents, so that's probably not going to crop up. All right, so we've got polar aprotic versus polar protic. So let's think about how they differ. So what we have to remind ourselves is, and we haven't talked about it much, but we need to remind ourselves what a hydrogen bond is. And so let's think about our nucleophile in the above case. So in the above case, we were using chloride as a nucleophile. So let's just draw a picture of our chloride. And so let's see. We'll do it on the same side. So we're gonna use the same nucleophile and think about how the solvent affects them differently. So now we've got our chlorides. And so let's use the polar protic first. And so I don't know. I'm gonna use water. Now water, of course, has a structure that looks like this, right? And so what we've got are dipoles going in this direction. All right. So when we think about water, is there any position on this water that's able to form a hydrogen bond with our chlorine anion here? Thinking back to about how. Well, first off, is it going to be the positive end or the negative end? It's going to be the positive end, right? So that sits with the hydrogen. That we know that we've got a partial positive on our hydrogens and then a partial negative on our oxygens. So that's pretty much our clue, because what's going to happen is we've got these lone pairs on chlorine. And so essentially, what can happen is we're going to have water molecules here that are able to form hydrogen bonds. And we just show a hydrogen bond with a dot here. So what is a hydrogen bond a full sigma bond? No, it's just a really, 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 really strong dipole interaction. So it's just a really, really strong intermolecular reaction between the hydrogen and the chlorine. And of course, we can have these pretty much all around our chlorine. Alright, so we're making all these hydrogen bonds to our chlorine. And so essentially, do you think that's going to make our chlorine more stable or more unstable? It's going to be stable, right? This interaction is not going to happen unless it's a thermodynamically favorable interaction. So we've got a full negative charge on our chlorine, and it definitely would like to have a little bit of positive charge wherever it can get it. All right, so this is pretty stabilizing, and in effect, what's going to happen is that the H2O forms a solvent cage around our nucleophile. So all that water is going to be attracted to the negative charge of the nucleophile, and it's going to form a little cage around there. And so it more or less, we can say that the nucleophile is more or less sequestered by the solvent. And so if the nucleophile is sequestered by the solvent, do you think it's going to be easier for it to break out of the cage and go to an SN2 reaction, or is it going to be harder? It's going to be harder, because for this to ever go be a nucleophile, it's going to have to shed all that water. It's going to have to push all the water away before it can go act as a nucleophile. And so what we find is that SN2 is not favored, because, again, it has to push all that water away before it can go act as a strong nucleophile. So basically, it's going to weaken the nucleophilicity. So at the end of the day, we find that with a polar protic solvent, SN1 is going to be favored. Boo, right? All right, so polar protic solvents are going to favor SN1 because essentially our polar protic solvents are going to surround our nucleophile in a solvent cage and kind of trap it such that it's not free to go act as a nucleophile. Gabby?
So do the other polar protic ones also form like the same cage?
Anytime we have an OH or NH bond, the hydrogen involved in that OH or NH bond is going to be the hydrogen that's involved in our hydrogen bond. Yeah. All right, so then when we look at the other side, when we have a polar aprotic solvent, let's use acetonitrile. I'm sorry, let's use acetone. So an acetone, do we have any OH or NH bonds on acetone? Nope. We don't, so basically we can't have that interaction. And so what's going to happen is, sure, we've got plenty of acetone that is solvating our chloride, but unfortunately, I guess really for us that's fortunate, because now our chloride will not be sequestered, so we can say that there's no solvent cage. And so the nucleophile is free strong. So in this case, SN2 is going to be favored. All right. So as an additional aspect of this, we're going to say that furthermore, SN1 prefers very polar solvents. Can you think of any reason why an SN1 reaction is going to favor a very polar solvent? Yeah, we're going through a charged carbocation intermediate, right? So a charged carbocation intermediate is going to be most stable in a very, very polar solvent where it can interact with one of the ends of that solvent. So we can say why? So that is because our very polar carbocation intermediate can be stabilized. Alright, remember from Gen Chem, like dissolves like, and so we can also say like stabilizes like. So we have a very polar protic solvent that has a relatively large negative partial charge. That's going to highly stabilize a fully charged carbocation and so ultimately make our SN1 reaction go faster. Alright. I think that's just about it. Yeah, that's pretty much it. Yeah.
So in a reaction, if you just gave us a reaction with the solvent, should we first look at the solvent to determine?
It'll be clear if I'm trying to ask you about solvent. I'll make it pretty clear that that is going to be the defining characteristic of the reaction. Yeah.
Is SN1 stepwise because of the caging? Is that why it takes longer?
That's part of it, right? I mean, so what it is that if we have a polar solvent that is going to be sequestering our nucleophile, basically, it's kind of like our date example, right? We said that in an SN1 reaction, you just say, forget the nucleophile is not coming, I'm going on out to the club anyway. Well, you can imagine that more or less the nucleophile has been sequestered by other romantic prospects. So yeah, the chain will pick you up yet. So, yeah.
Can you explain light dissolves light?
Polar things dissolve polar things, and non-polar things dissolve non-polar things. Yeah. All right, so we've got about 12 minutes. Do you guys want to do some review, or do you want to move on to the next material? You want to go to the next material? I can't believe how much you want to go to the next material. We're going to actually do a little review because I just feel like that's going to be more important for the next couple of days. So I love the enthusiasm, but all right. So let's see. Let's do some examples. All right. So for example, we have this right here, and we're going to use sodium cyanide. So now I'm going to give you a solvent. We're going to do it in acetone. And again, when you're doing these sorts of problems, what's the goal? SN2 is the goal. And so you want to try to do SN2. That's what we're going to see. We're going to see if there's any reason we can't do SN2. So we'll say SN2 is the goal. All right, so first off, what kind of halide do we have? It is a primary. Can we do SN2? Yes. Sure. All right, we're good there. Our nucleophile, sodium cyanide. Is that a good nucleophile? Yes. It is a good nucleophile. That's awesome. All right. And so just a heads up, whenever you see something like a cyanide, where's the negative charge? Is it the carbon or the nitrogen? Yeah, so that that structure looks like this. And so keep in mind, if you ever see cyanide, you're going to have reactivity at the carbon. That's the nucleophilic part of our cyanide anion. All right, so then let's see, we're also given a solvent. We have acetone. What kind of solvent is that? It is polar. What about protic or aprotic? It is aprotic. Are we going to encourage SN2 using an aprotic solvent? Yeah. All right, so we've got polar, aprotic. Is there any reason that we can't do an SN2? No, these are all great conditions to do an SN2 reaction, and so I could ask you for that, so you'd say this is definitely an SN2, and then you want to make sure that you want to draw in our new product, and it just looks like that, right? Pretty much swap out our iodine, stick our cyanide on there, and we're done. Yeah.
So if it was that same reaction, but instead of acetone, it was in water, would it be SN1 then?
I'm going to go ahead and just tell you guys that there's not really much on solvents on the exam. So I needed to cover it, but there's not much on there. So yeah. Probably shouldn't have told you, but yay. Okay. So then let's look at another example. Alright, so now we're going to do this reaction. So it's methanol. Alright, so what kind of halide do we have?
That would be a tertiary.
It's tertiary. Can we do SN2?
No.
Boo. No SN2. Alright, so that means we can only do SN1. Our nucleophile here, what kind of nucleophile is it? Yeah, it's a weak nucleophile. Furthermore, the nucleophile is the same as our solvent. Alright, so that means our solvent is also methanol. What kind of solvent is that?
Polar product.
It is polar product. Does that encourage SN1?
No.
It does, right? And so in fact, we're pretty much lined up here to do an SN1 reaction. Anytime that we have a nucleophile that is also our solvent, what kind of reaction is that? Yeah, that is given the special name of solvolysis. So if you ever see that, just basically your solvent is also your nucleophile in the reaction. Alright, so what we're going to end up with is we'd say, well, this is clearly going to be an SN1 reaction, and so I guess again, I don't know why I did this with achiral substrates. Alright, we're going to end up with basically adding in our methanol. And remember, initially upon addition, what we will have would be this. But of course, we always want to be able to get to a neutral substrate. So how do we do that? Deprotonate. Just like that. So that gets us to our neutral product. Everyone's on board there? Read?
So we just see MEOH with nothing else, and we know it's both. Like we don't see like another thing there acting as the nucleophile or the.
Yeah, I mean, if you only have methanol there, that's it. That's all you got, right? So you'll have to figure that out. But in that case, yeah, there's only one thing that can act as nucleophile. Yeah.
So, do we have to just draw the end product, or are we supposed to draw?
No, I'll have, and in this sort of example, I'll probably have a box here, and I'm just looking for the final product. What you just want to make sure is that this isn't your final product. You want to have a neutral final product.
Okay.
Yep. It wouldn't be racemic just because we don't have a chiral center, but if it were a chiral molecule, it would be racemic. Right, we don't have a chiral molecule because we don't have 4 different groups attached. The bottom part is the same ring.
How did you know that you don't, like, how did you know that it was solvolysis? How did you know that your solvent was your?
Because there's nothing else there, right? We know that methanol can be a nucleophile.
So if you were to draw 2 things, how would you know which was nucleophile and which was solvent?
Typically you'll often see the carbon but you know, you're never going to see something like acetone actually nucleophile, right? So in that case, you know acetone is just a solvent. DMSO is just a solvent. Yeah. Okay. Let's say. We have this starting material, and so we're going to react it with HBr. Alright, so this is a little different. Do we have a good leaving group?
No.
We don't. However, we're treating it with acid. Will that convert the OH into a good leaving group? It will, right? So in this case, what we'll have is this will convert to OH plus. And so what did we see? What type of mechanism is encouraged when we have an alcohol that's protonated? SN1. So that's a pretty big clue that we're going to go SN1. What's another big clue that we're going to go SN1? Yeah, what kind of carbon is this? It's tertiary, right? So we can't even do SN2 at all on a tertiary carbon, so we have to go SN1 here anyway. So in this case, we end up with this carbocation, and so what's going to be our nucleophile?
BR.
Yeah, so we have our bromine that was built in, and so we're going to have a tap of our carbocation. What we end up with would be this plus an enantiomer. Yeah. So there we've got a chiral center. So since it's an SN1 reaction, we'll add from both sides of our carbocation. Anyone got specific questions? I'm just going to work examples unless there's some questions. Yeah. It's racemic if it's this plus enantiomer. If it's that plus diastereomer, that's not a racemic mixture. So a racemic mixture is specifically two pairs of enantiomers in a 50-50 mixture. This would be a racemic mixture. It would be fair to call this racemic. Yeah?
But it wouldn't be racemic if it was like major. But you're not gonna ask us about this.
Yeah, well, yeah. So in this case, in fact, when it comes to racemic mixtures, it's because the products are pretty much the same except they're mirror images. Very rarely will you ever see one of these sides favored, and so when you have two enantiomers, it's almost always racemic. It's almost always 50-50. Yeah, Gabby?
I don't know if I can word this right, but so instead of doing like major and minor, because you're not doing that test. So if you ask us for all the products, it would just be like the resonance for carbocation products.
Yeah, keep in mind, when I'm talking about no major minor products, I can still ask you major minor about other reactions. It's just specifically with allylic halogenations, we're going to leave the major minor part out of those. Yeah. Okay. So for example, where that's actually, I can do a quick example of where that matters. So let's say we have this right here. All right, so what kind of halide is that? It's allylic, and so it is primary, but it's also allylic. Can we do SN2?
Yes.
Yeah, that's where we want to start. We want to ask, can we do SN2? And so we certainly could do SN2. Then we look at our nucleophile. Is it strong or weak? Yeah, we have a weak nucleophile, which means SN2, not going to happen. All right, so that means we can only do SN1. Now, can we do SN1 at a primary?
No.
We can't, but can we do SN1 at an allylic primary?
Yes.
Yeah, we can, and so we are able to do SN1 here. And so let's think about what will form from this. All right, so our stabilized, our resonance stabilized cation looks like this right here. And so we've got two areas reactivity. Now, which of these is, and this is just stuff that we already know, which of these is definitely the major contributor?
Right.
Yeah, definitely the one on the right here. So this is going to be our major contributor. And so which of these is going to lead to our major product? Yeah, definitely the one on the right. So in this case, we know we're going to get into this plus enantiomer, and then we're going to end up with a minor product over here of this. And so this is stuff we've already talked about, and specifically carbocations. We know that this is the major contributor, and so we're going to see most of our reactivity at the secondary position. So we'd say that this is major, and this is minor. So, but specifically with radicals, we're ignoring that part. Yeah. What's that? This one would not, because it's not a chiral center. Yeah. Okay. Any last questions? Office hours. I'm probably going to stop answering emails probably on like Tuesday late afternoon. So try to get your stuff into me before that. All right. Hey.
Hey. So I'm coming in Tuesday at noon.
Yeah. Yep.
You guys can go first. So
why would the Cl minus be a good nucleophile? Because it's a good leaving group, right?
Yeah, so the thing is I've talked about how basicity and nucleophilicity aren't totally the same thing, and so that's a case where they very much diverge. We find that chloride, it's the conjugate of a strong acid, and so it's a great leaving group. It's also really nucleophilic. And so again, remember that basicity is based on a thermodynamic property, nucleophilicity is based on a kinetic property.
Okay, so is it because it's charged that it can bind?
It's charged, it's relatively big, that makes it a good nucleophile, but it's also very stable on its own, and that makes it a good leaving group. So yeah, no, it's definitely kind of weird.
Yeah.
So we talk about how we want the SN2 reaction.
Always try to do SN2. Don't.
So is that because like in practice that is what like physics favors?
It's typically faster, yeah. Because if we go through an SN1, we're going through a carbocation.
Yes.
And so it's usually slower to go through a carbocation.
So we like it, and also it like okay.
We like it. We get less products. It's the way to go.
Thank you.
For the extra time, can I just between your almost 10 after?
Let's see. Yeah, try to. Do you want to come in like 10:15 or something?
I have class right after this morning,
Okay.
so,
You can do it in the afternoon. Yeah, email me so I'll remember. Yep. Hey.
Okay, so for this, the last one, what we did was we deprotonated, so we made it a good leaving group for the alcohol.
We didn't make it a good leaving group. What we did was we put a negative charge on it, which makes it takes it from a weak nucleophile to a strong
Okay.
nucleophile.
And then previously, the first thing we did was protonated.
And that was to make it a good leaving group.
But it was still not a good enough leaving group to do SN2. You had to do SN1.
Right, so that's why then we used the tossal group so that we could do SN2.
Right. Okay. And so on the test, would we have to be able to like tell the difference between all those products?
Yeah, I mean, we didn't talk much about this. So this is just a way I wanted to show that we can, in fact, convert a bad nucleophile into a good nucleophile by deprotonating and putting a negative charge on. It's definitely going to be more important to think about the alcohols as leaving groups.
Okay. Would we need to know how to, like, would you give us something with an alcohol and we would need to decide whether we would use the TCl or the deprotonating?
I don't know if I can tell you that.
Okay, so like
It's possible.
try and figure out the difference between those.
Yeah, spend a few minutes on it, but don't spend a ton of time.
Okay. Do they all end up with the same product?
It depends. If you protonate, you're going through the SN1 mechanism.
Right. Okay.
If you tosylate, you go through the SN2 mechanism.
But that would be the same thing as if we had done this.
So this it doesn't. We're going to get completely different products because now we're reacting this as the nucleophile. So in the other case where our OH is leaving, that's the electrophile. But now when we put a negative charge on it, now it's the nucleophile that's going to attack another.
Oh, that's going to attack something different.
Yeah.
Okay. All right. Thanks. That's all.
And a quiz.